Hi everyone, this is Mona Sinhaji from Jacobs Engineering Group. The project that I'm going to present today is the topic of my master's thesis at Illinois Center for Transportation, UIUC, under the supervision and guidance of the Professor Imad Al-Qadi and Dr. Hassan Ozer. The project was funded by Federal Highway Administration and actually it's part of the efforts of Federal Highway to help state and local agencies in implementing sustainable assessments in their decision making, especially at the network level. So the outcome of this project was a developed life cycle assessment tool for in-place recycling techniques. This work is a collaboration with University of California, Davis, as well as Rutgers University. The motivation from this project is a need to develop a generalized methodology to compare the environmental impact and energy use of in-place recycling techniques and conventional methods. So for those who don't know what in-place recycling techniques are, it's actually we're using the materials of the existing pavements for maintenance or rehabilitation. And of course, this pavement is milled and mixed with other asphalt or non-asphalt agents as needed, depending on the type of in-place recycling, and also depending on the project conditions. The conventional pavement methods are the traditional milling fill. So the research methodology was collecting data, especially the construction data from state agencies and contractors around the U.S., especially the contractors who have experience with in-place recycling techniques. We developed a methodology and framework for in-place recycling and conventional methods, life cycle expectancy models, which were developed by Professor John Harvey from UC Davis. We developed also regional life cycle inventory for all resources, and finally developed a user-friendly tool using Visual Basic. So this tool can be applied on a national scale and will allow agencies and contractors to assess in-place recycling alternatives based on LCA. So below you can see screenshots from the tool, which is actually on Excel, but the user will be able to navigate through the tool using interface. 35 maintenance and rehabilitation treatments were considered in the tool, including surface treatments, in-place recycling techniques, and conventional methods. So when I say here in-place recycling techniques, for example, it's not only cold in-place recycling applied by itself, but also we have other combinations of in-place recycling with surface treatments like cape seal or chip seal, and also with asphalt overlay and with different type of thicknesses. The same applies to conventional methods. And just back to this treatments that we are including. So these combinations, we provided them to be close to what we apply on our highway project. The LCA system boundary that we are considering in this tool comprehends all the life cycle stages from material production and hauling to the end of life. For the analysis period, this is a key parameter to conduct LCA, and it needs to be defined as a goal and scope. The analysis period is crucial when it comes to providing maintenance and rehabilitation schedule, which we provide in the tool, and also effect on the use phase impacts, which are the most significant impacts in all the life cycle of the pavement analysis. So the way it was calculated is using FHWA pavement LCA framework that was published in 2016. So here we provide an example in this figure. If we have 5 alternatives for maintenance and rehabilitation, we calculate the analysis period based on the longest living alternative. Then we look at the subsequent maintenance or rehabilitation, and then we truncate the analysis period at the end of that treatment. So again, we look at the longest living alternative, then the next treatment that we apply after that. For the inventory data analysis, I'm going to present here the questionnaire responses, the number of questionnaire responses that we got from state agencies and contractors around the US. The contractors, again, are the ones that have experience with in-place recycling techniques. And this is, these are the contractor questionnaire items. Of course, this questionnaire, we had another questionnaire that was developed for agencies, but for the contractor one, the items were focused on the project information, materials, fuel usage, construction equipment, and the data that we collected from the contractor was very helpful to understand what parameters affect the most on the fuel efficiency during the construction stage. So here is an example from cold in place recycling data that we got from a contractor. And clearly, the milling operation, which is in green, contributes the most to the fuel consumption during the construction stage. But other variables affect also on the efficiency, including the hardness of service materials, the temperature during construction, depth of milling, and width of pavement. These variables were, or these factors, were defined based on the data analysis that we conducted, but also through the communication and confirmed with the communication that we had with the contractors that we collected the data from. And later on, we're going to see in the case study some of the impact of some of the variables. For the life cycle inventory, we developed a regionalized life cycle inventory model for fuel and electricity production, material production and processing, hauling and transportation, and equipment usage. For the construction model, we developed a non-road model, which is on-site, in-site equipment model using MOVE 2014A from EPA. And the parameters, so the user has to select the equipment category, the fuel type. For example, for hot in place recycling, some of the equipment will use propane, for example, the preheating unit. And for other treatments, for other equipment, they use mostly diesel. The user will select, of course, the construction year, the horsepower range, and finally the tier category. So what I mean by tier category is emission regulations that EPA has on certain equipment, and it is mainly affecting on restricting the emissions from oxides from NOx and particulate matter. The hauling model developed was using MOVE 2014A on-road, and the parameters are vehicle weight, road weight, temperature, and relative humidity. The model that was developed at Illinois Center for Transportation is the VIT at the end. And we can see that in this model, we're considering grade, which is a significant variable to assess hauling impact. And this model helps us also regionalize the assessment that we're conducting during the hauling stage. So if we set a study to compare the hauling impact in Illinois versus California, you can see the difference. And we'll see that in the next case study that I will present. It is also important during for the LCA that we're conducting to estimate the life expectancy of each treatment selected by the user. And also that will help us to develop the use phase, IRI progression model. So two approaches were developed. The first one is deterministic performance models, and that was developed by UC Davis. These deterministic models are very specific, are region specific, and they were specific to California. That's why in the tool, we gave the user the ability to input their own parameters. If they don't have available deterministic performance models, they can estimate the life expectancy using multi-criteria performance estimation, which is based on a decision matrix that was developed based on site-specific conditions. So each of the 35 treatments that we are considering in the tool is scored out of 5 under different conditions, under different distresses, kind of distresses, different PCI, pavement condition index, different climate type, road type, and that's a way to mitigate to any non-availability of deterministic models. So at the end of this multi-criteria performance estimation method, the user gets a performance score for the treatment selected, and that will also affect on the estimated life for the treatment. So here I'm going to present a case study just to give you an idea of the factors that affect on the energy savings that we make when using CIR versus conventional methods. Here, these are 2 equivalent designs using the modified ASHTO Chapter 46 from IDOT. Here we have 2 equivalent in-place recycling and conventional alternatives. This figure shows the energy savings that we make when using CIR versus mill and fill. Of course, the longer the hot mix and mixed asphalt hauling distance is, the higher are the savings that we make when using in-place recycling techniques, because there is no need in in-place recycling to haul the mixes to the job site. Also, we can see here the difference between a flat grade and a stiffer grade. So let's say we are in Illinois at 0% grade versus in California for 8% grade. The in-place recycling will be more effective to use. So which make the regionalized models very important, and they affect a lot on the efficiency of the treatment selection. And also from another aspect, if we look at the hardness of the pavement, we developed a fuel users model for that accounts for hardness. And if we make the pavement harder, we can see that there is a drop of 3% of the energy savings of CIR versus mill and fill. And this is due to the fact that for the CIR treatment, for the design here, we have 3-inch CIR versus 2-inch HMA mill and fill. So here we have, for CIR, we have a deeper thickness to mill, and the milling efficiency is very related to the hardness factor. So overall, the in-place recycling condition, the job condition affects a lot on the how effective is the in-place. It's not about just recycling. Recycling pavements is not always like the optimal solution for maintaining or rehabilitating the pavement. It's actually a decision that needs to take into account the project conditions, and of course, along with the cost, along with the social assessment. As a summary, this tool is based on life cycle methodology that was developed to allow comparing various preservation and rehabilitation alternatives. And the process activity data collected from in-place recycle contractors were integrated into the life cycle inventory data and models. And finally, whole regionalized hauling and construction models were developed for the energy use and environmental impact. So that concludes my presentation, and I'm open to your questions.
Hi Mona, thank you very much for a very nice presentation, and really appreciate you demonstrating the tool. One question that I had, we also have some questions from audience, but is the tool available for others to use, and if so, what would be the best procedure, what steps should we follow in order to obtain it?
So the tool will be available. We didn't receive yet the date when it's going to be released, but it's going to be for public use. So there will be no restriction to use it. You will not need any license. But we didn't receive yet from Federal Highway when it's going to be open for public use. But the LCA tool will come with a user guide, which will help the users navigate through the tool and conduct. So the outcome of the tool will be a maintenance and rehabilitation schedule provided, along with, of course, the environmental assessment of each of the alternatives that will be selected by the user. And just for information, this tool, the user will have the ability to select up to 5 treatments to compare at the same time. So that's why I'm saying in the summary that it allows not only conducting environmental assessments for in-place recycling techniques, but for various preservation and rehabilitation alternatives.
Wonderful. Thank you very much. And we do have some other questions, but I'll email you those just in interest of time. So we'll continue on with the next presentation. Thanks again, Mona. If you could just turn your screen share off, then the next person should be able to share the screen.
All right. Thank you.
Yep.